So this is problem 78 from chapter 29. Now here we have some ring that has a capacitor on it and a resistor, and it forms sort of a circle. These are labeled VB and VA, and we have a resistance of R over here. This whole thing has radius R, and it is immersed in a magnetic field that's perpendicular to the plane of this loop. So it's a uniform but time varying field, so it's same, but its magnitude is changing. Okay, so let me read the question. We have a circular-shaped circuit of radius R containing a resistance and a capacitance C. Is situated with its plane perpendicular to a specially uniform magnetic field B directed into the page. Starting at time t equals 0, the voltage difference VB minus VA across the capacitor plates is observed to increase with time t according to VBA is V0 1 minus something. Okay, so VBA, which is defined to be VB minus VA, is increasing with time minus t over tau with this formula. Okay, so at t equals 0, this exponential becomes 1 minus 1 is 0, it's 0, and then as t goes to infinity, this exponential just disappears. This is going to be just V0. So we have something like this. So V is a function of time. If we call this V0, some asymptote here, it's going to reach this asymptotically as an exponential curve. Okay. And V0 and tau are positive constants. If we are asked to determine dB by dt, the rate at which the magnetic field magnitude changes with time, and is B becoming larger or smaller as time increases. Okay, so we are asked dB by dt, it's this, and whether it's increasing or decreasing. Now I think so this is an involved problem because it puts together stuff from a lot of concepts. So we obviously have some changing magnetic field. That changing magnetic field leads to some induced EMF, and that EMF is going to drive some current over here. That current charges the capacitor, so this acts like an RC circuit. It's just a few concepts thrown together, but it's a nice problem. It's not an unfair problem. It just requires you to know things from different concepts. So is B increasing or decreasing? So if this potential, if this point is reaching a higher and higher potential with respect to this point as time passes, then we must have a current that's going this way. Okay? Now, a current going that way is, so if this is the current in our loop, is going to produce a magnetic field into the plane of the blackboard or into the plane of the page of the book. And so since this must be compensating for the change in the magnetic field, our B must be decreasing. Our B is initially also into the plane of the blackboard. Since the induced current is also into the plane of the blackboard, that magnetic field must be decreasing. So B is decreasing. Okay. This we can just argue from Lenz's law without doing anything else. Okay, now, but we are required to find this dB by dt, and of course that dB by dt times the area of the loop is going to give us the change, the induced EMF in the loop. So that's going to be that's how we are going to calculate this induced this rate of change of magnetic field. So this one times the area of this loop, pi r squared, is going to be the induced EMF. Now what is that induced EMF? Well, that induced EMF is both the potential across this capacitor and the current that's just passing through. Okay, so how do we calculate that current? So if this is how the potential is changing, now this is a capacitor, so its capacitance is just Q by delta V. So that delta V must be Q over C. So by knowing how this changes, I can say how the Q is going to change. So perhaps it's easier to write it C times delta V, and so this is going to be some C V0 1 minus d t over tau. Okay, so this is how the charge across the capacitor changes. So Perhaps we can call this Q0, something like that, if you want. And that is going to have the same behavior. The derivative of that charge must be just, moving through this resistor. So the rate of change, the rate of flow of that charge is going to be our current. So the Q by dt is going to be our current, and that is going to be just this C V0, and the derivative of this is going to be just minus e to the minus t over tau divided by tau. Right? So this derivative of 1 is 0. This brings a factor of minus 1 over tau. This cancels partially with this minus, so it becomes plus. So this is e to the minus t over tau divided by tau. So this is my current, and this is going to correspond to some. Potential change across this. I already know the potential difference across that one, so the sum of those two is going to give me the total potential difference. So I need some more space, perhaps I can write this. So the EMF induced is going to be the delta V over the resistor plus the delta V over the capacitor, and the delta V over the resistor is just R times I plus this, BBA business. So let's write this down. This is going to be RC V0 over tau e to the minus t over tau. This is just R times I. I need also the I here. Oh no, this is already I, sorry. This is t over tau. So C R0 and R over tau, okay. And plus this whole thing over there, plus V0, 1 minus e to the minus t over tau. And this must be equal to the rate of change of magnetic flux. So let me erase this. I am running out of space, unfortunately. This is going to be d phi b by dt. And that must be because the area itself is constant. It must be the area times the rate of change of magnetic field. So this is pi r square dB by dt. Okay. Now I can take this left-hand side and I can rearrange it. I can put this into some common parentheses. So let me erase this and write that expression more clearly. So I'm going to have e to the minus t over tau RC V0 over tau minus V0. Okay, so it is this term plus V0. Okay, so this is the whole thing, and this must be equal to pi r square dB by dt. Now, can we simplify this further? That is one question. So in particular, if tau is equal to RC, then this term completely drops out and you have a simple expression for dB. But is tau equal to RC? Okay. It could be, and I think in the solution manual they are just making that assumption and just proceeding that way. However, it's not obvious that tau should be equal to RC. It would be equal to RC if this rate is constant. Okay? So you can show that somewhat trivially, that you just take the derivative of this equation, and then if this is a constant, then this part just drops out. You get some equation. So let's proceed that way. So if I take the derivative of this, then the right hand side is 0, this term is 0. This is going to introduce a term, and yeah, so we're going to get e to the minus t over tau divided by tau RC V0 over tau minus V0 is equal to 0. If I take the derivative of this, then of course, if this is 0, this must be equal to 0, from which it follows that RC must be equal to tau. However, when I take the derivative, if the right-hand side does not vanish, if dB by dt is not constant, if this magnetic field is not changing at a constant rate, then it doesn't follow that tau is equal to RC. Now it does follow that this must be changing. If it's not constant, it must change as an exponential, right? So you can actually calculate it, but they're not giving us what it is. And I think they mean that this rate of change is constant, so you can actually make the substitution, and this term just drops out. You can get a simple expression for dB dt. But if you get confused by the fact that the solution manual is just assuming tau is equal to RC, well, you're not alone. This is not obvious, and it's not necessarily correct. It is correct, however, if this dB by dt is constant. So if the magnetic field is decreasing at a constant rate, then tau is indeed going to be RC, and we get a simple expression as given in the solution manual. Okay, I think that's all.